So the next section is big O notation. So big O notation came from looking at polynomials of degree n as x goes to infinity. So now the n is fixed, but it's the argument of the polynomial, the x value that's going to be getting large. And I want to have a measure of how fast this polynomial is getting big. And so it turns out that, so this should be as x goes to infinity, the highest order term dominates the other. So what I can do is look at the limit of my polynomial as x goes to infinity divided by x to the n. So x to the n is the highest, it's a x to the highest power. It's x to the degree of the polynomial. So I can write my polynomial like this. It's just the sum of a coefficient times, or a constant term plus a coefficient times x plus a coefficient times x squared and so on, up to a coefficient times x to the n. So that'll be the last term. So there's one term in the numerator here that's a coefficient times x to the n. And then I'm going to divide that sum by x to the n. And what I'm going to get is one term that's a sub n times x to the n divided by x to the n. So that'll just be a times x to the n. And then each additional term, because the part on top is to a power smaller than n, the x is going to move down to the denominator. And so as I take the limit of each of these terms as x goes to infinity, each of these terms is going to be getting smaller and smaller and smaller, while this a sub n, the coefficient from the xn term, is going to remain constant. And so when I actually take this limit, what I'm going to end up with is a to the n. And so big O notation is just trying to summarize this behavior in a simpler way. And so I'm just going to say that the polynomial p of x is big O of x to the n. So the way you can sort of think about this is if you looked at x to the n, or the polynomial, and just sort of zoomed out, what is this going to look like? So if you were, if you're at a very small scale, all of the terms are going to contribute something. But suppose I was just looking at x squared plus x plus 1. When I evaluate that at the point 1, I'm going to get 1 plus 1 plus 1. So each term is contributing equally. When I evaluate it at the point 1,000, now the x squared term is contributing 1,000,000. The x term is contributing 1,000, and the constant term is contributing just 1. So on kind of a percentage-wise bit, that's the million is dominating that. And so as I zoom out, all I'm really going to see is a parabola. And whatever effect the x and the 1 have at a smaller scale, they're just going to disappear as I keep moving to larger and larger scales. And so because that polynomial would look like a parabola as I sort of zoomed out and just continued zooming out, I'm going to say that that would be order of x squared, or order x to the 2. And so formally, the way we're going to define big O notation is let f and g be functions, so they're functions from the real numbers with a real output. And then I'll say f of x is big O of g of x as x goes to infinity if there is some constant c and some constant m, both greater than 0. So I'm not really concerned with sign here. All I'm concerned with is just relative magnitude. So if f of x divided by g of x, as x is getting larger and larger and larger, if this ratio is bounded by a constant, so for instance in the last example it was just this coefficient on the highest degree term of the polynomial a sub n, whenever x is greater than some fixed real number, so that this is just me trying to take advantage of the definition of a limit, then we'll say that f of x is big O of g of x. So they grow at the same rate after x exceeds some threshold. similarly, we can sort of spin this around for finite points. So generally, when I'm thinking of x going off to infinity, I'm thinking of things getting bigger. So the function of x is getting bigger, and I'm interested in, are f and g growing at the same rate, up to a constant of proportionality, or is f growing, at some faster rate? So, if f was a polynomial of degree 3 and g was a polynomial of degree 2, then there wouldn't be a value c that kept this bounded. On the other hand, when I look at a finite point, so now I'm thinking about x going to a rather than x goes to infinity. So I pick some real number, a, and I want to think, how does f of x behave as I move closer and closer to a? Then I still want to have this constant c, which is sort of my constant of proportionality. But now I'm going to have a width delta. And so I want to say that f of x and g of x, so f of x divided by g of x, the ratio of that magnitude, is less than or equal to this constant of proportionality whenever x is within delta of a. So in some neighborhood around the point a, f of x and g of x have the same. So when it goes to infinity, I say sort of growth characteristic. Here I suppose I should say it shrink characteristic or something like that. And so what I'm after in this case with the second definition is I want to understand how big the Taylor approximation error is. And so I want to understand that as the point where I'm making my approximation gets closer and closer and closer to the point A where I've built my approximation. And now, so if I'm looking at things getting big, quadratic or cubic, that's sort of bad. That's saying, well, x is already getting big, and x squared or x cubed is getting big much, much faster than that. And in that case, it would be the highest order term that's sort of going to dominate. When I look at things getting small, so if I take 1 and square it, I get 1. If I take something smaller than 1 and square it, I get a number smaller than what I started with. And so there, it's going to be the smaller power that's going to be the dominant one. And so what I want to be able to show here is that the Taylor approximation error is big O. So the distance between the point where I'm evaluating my Taylor polynomial and the point A where I've constructed my Taylor polynomial. The larger I can make this number, the faster this error is going to get smaller as I move towards A. So once I'm sort of within 1 of A, this quantity is going to be less than 1. And when I start taking powers of that, it's going to get small. And then the larger the power I can make, the faster this is going to get small as I move closer and closer to A. So I can also just rewrite this as one of the terms in my Taylor polynomial approximation. So I've said that f of x minus the approximation at x is order x minus a to the n plus 1. And this is, again, as x is going to a. So it's not trying to say how bad does the approximation get as I move away from a. It's trying to tell me how good does the approximation get as I move towards a. And I can just add the polynomial to both sides. So I move the p sub n of x over to the right-hand side of the equality. And then replace that with the definition. And so what you see is here I have the constant part of the approximation. Then I would have the linear part of the approximation, the quadratic part of the approximation, and so on. And I end up with my last term being the sort of nth degree approximation term. And then the amount that I miss by is going to be on the order of x minus a to the n plus first power, again, as a is moving towards x. And what this allows us to say is, for instance, the linear approximation. So here's my Taylor polynomial of order 1. So I have a constant part of the approximation, and then I have the linear part of the approximation. And then what's left over is big O of x minus a squared. And the quadratic approximation then is going to be a third order approximation because both so where this term is coming from is from either the derivative form or the integral form of the Taylor approximation error. So I have that x minus a cubed is the size of that's describing the growth of the approximation error, how fast it, I suppose, shrinks as x goes to a. And I don't really care about the constant of proportionality. I just want to know if I use this approximation and then I move twice as close to a, this term is going to get smaller at a cubic rate. And so again, the larger I can make this power, so this is just me adding more terms, then as x goes to a, means I'm getting closer and closer to the thing that I want to be getting at a faster and faster rate, so as this number gets bigger.